Today I'm going to be talking to you about what I call navigating the design space of trajectories towards low and zero carbon energy systems in California. Fancy title aside, what that really means is that we have a lot of different options and a lot of different ways that we can meet these goals that California has set for high penetration renewables, for greenhouse gas emissions reductions. There's lots of specific policies set for that. And we really have to start looking into not just comparing going to those goals compared to business as usual, but looking at different trajectories that can meet those goals. What are the pros and cons associated with those? And what, more importantly, what are some of the unintended consequences that we might run into by choosing certain pathways versus others, and how can we avoid them? So just an outline, just some introduction, motivation, and context, which for this crowd, I'll probably be preaching to the choir. But really, my talk is going to focus on these two examples, which are two kinds of strategies or two kinds of technologies that we're really looking to deploy to help meet these goals, but also looking at ways that deploying these technologies can turn out to be a disbenefit and ways that we can avoid them. And then I'll conclude. So first, we'll talk about some motivation, preaching to the choir here. There's a large concern about environmental sustainability. We've all figured out that the current configuration of the energy system, which is fossil fuel based, has all kinds of environmental impacts, and that includes not least climate change, but there's also more regional effects such as air, water, and land pollution here in the US and other countries in the world. But there's also the dimension of resource security, right? So historical events have shown that our supply of resources that we need, energy, and in California especially water, is vulnerable to a lot of different things, right? There's vulnerable to geopolitical instability. When gas prices first started to go up in the early to mid 2000s when I was in high school, that was like a big shock, right? And that's all geopolitical, what's going on there. There's sustained drought. Drought affects water supply directly, but it also has effects on the energy infrastructure due to affecting hydropower generation, due to affecting how much pumping we're using for groundwater and so on. And then there's also different kinds of infrastructure vulnerabilities to shocks like natural disasters, to cyber attack, things like that. So in addition to the sustainability focus, we really are also looking at resource security, which is two main reasons that we've motivating this transformation. So in California, the most recent policy that has been passed is Senate Bill 100, where by 2045, they want to have a 60% minimum renewable grid and also a 100% zero carbon grid by 2045. This is a relatively old executive order, but this focuses on an economy-wide greenhouse gas emissions reduction of 80% below year 1990 levels by the year 2050. And one thing that's also important for the Institute of Energy Efficiency is California also has a lot of regulations for zero net energy mandates on buildings, right? And technologies, especially control technologies, are going to be very important for helping meet those. These include all new residential homes must be zero net energy by 2020, all new commercial buildings by 2030, and 50% of existing commercial buildings also by 2030. So the rest of my talk is there's a lot of different things that we can do to help meet these goals. There's lots of technologies, there's lots of variations on those technologies, there's lots of control strategies. In the electricity sector, there's different kinds of energy conversion devices, all kinds of renewables. There's supporting technologies and management strategies like demand response, energy storage, advanced power plants, and so on. In the light-duty transportation sector, there's increasing levels of electrification through plug-in hybrid electric vehicles, battery electric vehicles, fuel cell vehicles, advanced gasoline vehicles, perhaps not as much anymore, but that's still important for people that need gasoline vehicles. And then in the water supply sector, even though I'm not focusing on this aspect in my talk today, but there's also measures that we can take there like conservation, different kinds of desalination, and water reclamation and reuse. So with all of this in context, the major questions we have to think about are, how do we choose between different technological pathways for achieving these outcomes, specifically these policies in California? What are some of the obstacles that we might run into and unintended consequences we may encounter when we just go full on with deploying a lot of these technologies, and how do we avoid them? What are some of the solutions that we can employ to avoid or mitigate some of these consequences? So, as I said, I'm going to focus on two examples, the first one being the large-scale electrification of light-duty transportation, specifically in California. looking at it from the perspective of grid integration and achievable greenhouse gas emissions. So, large-scale electrification of transportation. A couple of questions in this context. What are the impacts of large-scale deployment of alternative powertrain vehicles in the electricity system? We've heard perspectives earlier today from California Edison, looking at the grid side. There's all kinds of work that looks at impacts on drivers, so on and so forth, range anxiety. And what needs to actually be done to realize the potential benefits of these technologies for meeting these environmental outcomes? So just as a disclaimer, the content I'm about to present is from a bunch of papers and reports coming out of our group, so we can talk to you about that later if you're interested. So let's start with just looking at the potential of electrification for vehicles. What we have here is this is the kilograms of greenhouse gases per mile in carbon dioxide equivalent of different kinds of vehicles using different MPG values for the gasoline vehicles and BEVs plugged into different configurations of the electric grid, right? And what we can see straight off the bat is if you go from, say, a 25 mile per gallon average, which is the current present day fleet average, down to everybody driving BEVs plugged into 100% renewable or at least 100% zero carbon grid, we can get pretty significant greenhouse gas emissions reductions. Even going from a 40 mile per gallon vehicle down to using BEVs, you get pretty significant reductions. So with advances in decarbonization of manufacturing, which is this blue bar, we can get even lower, right? So there is huge potential here in greenhouse gas emissions for deploying alternative vehicles, which is why there's a lot of incentives for those. But it's important to remember that in order to realize greenhouse gas benefits from electric vehicles, there are some other considerations. As we talked about earlier, recall that to utilize renewables, electric loads have to match the renewable generation profile, or you have to put in systems such as smart charging and energy storage to shift one to match the other. And if we do no management, this is a study that we have in 2050, we have a large amount of renewables, and we've turned over 90% of the vehicle fleet to entries that are going to be in this column. We start here with the reference in 2050. This is the everybody drives Prius's case. If we deploy plug-in hybrid electric vehicles and battery electric vehicles, each of these configurations represent how these vehicles are integrated with the grid. So we have immediate charging, where you go home, you plug in, it starts charging at full power until the vehicle is full, and then it turns off, right? Then you have smart charging, which is grid communicative. Then you have charging at home versus charging at home and work, and then also installing energy storage. What you notice is if you go from everybody drives Priuses, or 90% of the people drive Priuses, to 90% of the people drive 200-mile BEVs, and you have no charging management, this is immediate charging at home only, you get almost not very much greenhouse gas emissions reductions, right? And for all this effort installing all these renewables, turning over 90% of the vehicle fleet, and this is all the greenhouse gas emissions reductions you get, it's like, why did you even do that, right? And this just shows the issues associated with if you don't manage your charging, these are some of the unintended consequences you'll run into. You're not going to get the greenhouse gas emissions benefits you're thinking of, and that's because real-world greenhouse gas emissions reductions are affected by a couple of different factors. Where is the charging infrastructure available, right? If you want to charge during the day, but then there's not charging infrastructure at the place where your vehicle is plugged in or your vehicle is parked during the day, you're not going to be able to help with that, right? There's also charging management intelligence, right? If you're just charging at full blast whenever you plug in, there's no sort of optimization or consideration of what's going on with the grid, with renewable generation, with electricity prices, and so on. So immediate charging at home, that worst case I talked about here, this is a profile of the charging load associated with a few vehicles throughout the day. You notice there's load during the day, some people are charging during the day. Most people charge when they get home from work, they plug in, then they also go inside and turn on their TVs and start cooking. So it coincides with the residential peak, and that's very bad for transformers, so our SE colleagues can attest to that. And if you look at where vehicles are, they're mostly at home, they go to work, sometimes they go to other places, but it's really home and work that dominate the distribution of where vehicles are during the day. And what that gets you is, here's a mix that has a lot of solar, it also has a lot of wind, but this black line is a renewable generation profile in aggregate. This red is the amount of solar that gets curtailed, and this light blue is the EV charging load. And what you notice is that the EV charging load doesn't fall inside the envelope where there's a lot of renewable generation, right? So we have to manage that, right? And that's why you only get that far. So there are things that we can do to manage this, right? But first, an unintended consequence is, if you don't manage your charging or if you don't have energy storage, consumer travel patterns will limit the potential greenhouse gas emissions reductions you're going to get from deploying EVs, right? So how do we get around this? Let's look at smart charging. Now, what I mean by smart charging is a paradigm where consumers plug their vehicles into the grid, then they also schedule some information about their travel patterns into the grid. In this case, they plug into the grid and they say, okay, my car is going to be parked for 4 hours. By the time I unplug, I need at least 100 miles of charge. And with that information, grid operators, whether it's the utility or the balancing authority or whichever entity, can dispatch and maximize charging when there's renewable generation or if prices are low, and minimize charging otherwise, under the constraint that you do ensure that the consumer has enough charge to meet their next trip, right? So if you do that, you can align the charging load a lot better. In this case, it's going to maximize charging during the day, assuming you have charging at work. And you can get a large amount of greenhouse gas emissions reduction, right? Now, going from most people drive Priuses to most people drive BEVs, this is the same amount of vehicles, the same amount of renewables. Maybe there's a little bit of extra communication hardware, but for the most part, this is the same hardware installed on the grid, and you're just managing it better, right? And that's how you realize those potential benefits I talked about in the beginning. But smart charging might have some issues associated with it, right? So I teach a class in sustainable energy systems. I've been teaching it 6 years now, and every year I ask the students how many of you would be comfortable telling the utility or so on information about where you're going to be and how long you're going to be there for the next 12 hours. And no one raises their hand, right? Actually, no, I think 1 year one person raised their hand. But these are students taking a sustainable energy class who are interested in sustainable energy, right? So if you look at the general public, there may be some issues with getting buy-in, right? There has to be proper incentives to get buy-in, because it interferes with consumer convenience, poses some privacy issues. There's also the aspect of if you let an external operator control the charging of your battery, in this case with smart charging, or going further if you do what's called vehicle to grid, you're letting an external entity control the charging rates and then with V2G discharging rates of your battery, which degrades an asset that you own, right? It degrades the battery. So how do you get compensated for that? And it doesn't leave as much room for unscheduled travel, right? If you tell the utility what your travel patterns are going to be and then you deviate from that significantly, you would probably get penalized, right? And I think a lot of people don't generally like that. So if we can't get consumers to smart charge, we'll need energy storage. And energy storage kind of does what you expect it to do. It will charge and make use of its otherwise curtailed renewables, discharge it when the EV charging load occurs, and you get pretty good greenhouse gas emissions reductions. The larger amount of storage that you have, the more reductions you get up to a certain point. But it's important to remember that doing it with storage has a cost, right? Storage doesn't just magically appear out of nowhere. It has embedded energy, it has an environmental footprint, it has a cost. So we really want to do things to minimize the amount of storage that we need, which I'll talk about in my second example. Oops, yeah. So moving to the second example, let's talk about large-scale deployment of energy storage. And energy storage is something that's very popular right now. So when thinking about deploying a lot of energy storage, we have a couple of main questions. First is, how much storage do we need, right? There's kind of this assumption that we'll just deploy batteries or we'll just deploy storage everywhere and then it'll eventually solve itself. But how much storage do we actually need to meet California's energy and environmental goals? And if we deploy that amount of storage to scale, what's the net benefit associated with that? If we include that environmental footprint and life cycle signature of energy storage, are we shooting ourselves in the foot? And that's what we'll talk about. So also disclaimer, most of this content is coming from a couple of papers we published. Some of the slides we'll present at the end are from preliminary results for a paper in public or that are to be submitted, so please don't cite it quite yet, but we can talk about it, which is because it's interesting. So energy storage is a key component of enabling renewable resource integration because wind and solar are very popular, right? And wind and solar have the largest technical potential of different kinds of renewable and zero carbon resources, just planet-wide on an exergy basis. So energy storage is needed to harness them because of their variability. So when you start to ask the question of how much energy storage is needed, that depends on a lot of things, right? So fundamentally, what does energy storage do? Energy storage compensates for the misalignment between when generation occurs and when load occurs. If that misalignment is really bad, you need a lot of energy storage. If that misalignment is perhaps not as large, you don't need as much energy storage, right? So before you can answer that question, you have to think about how much of your generation portfolio is dispatchable and flexible to be able to meet loads. If you have things, say, like biogas or hydropower that can just meet loads directly in a zero carbon-ish way, you need less energy storage. Also, if you have flexible loads, and this is where a lot of the control systems being worked on in the Institute of Energy Efficiency can help a lot. If you have a lot of loads that are flexible enough and you can shift them to occur when renewable or low carbon generation is occurring, you need less energy storage, right? So to get at this question, I'm going to start with a very, very extreme example of what if, for some reason, we wanted to reach 100% renewables in California using wind, solar, and storage only, and absolutely nothing else. This is the extreme bounding case for how much energy storage you need. And we get a graph like this. So on the y-axis, we have the wind and solar energy penetration, and on the x-axis, we have the energy capacity of the aggregate energy storage system on the California grid as a percentage of the annual electric load. And I'll translate these to actual numbers in a little bit. But first thing that we notice is if we go from no energy storage, we can still get pretty high if you just deploy a lot of renewables. This is 20% overbuild means 20% more renewable capacity than we need. 50% means 50% more renewable capacity than we need. If you deploy just a lot of renewables, you can get pretty high. And when you go from no energy storage to the first unit of energy storage, you get a pretty large boost, right? And that's because most of the misalignment occurs on a diurnal time scale. Once you have enough energy storage to shift over the course of a day, you are able to utilize most of the curtailment. But renewables also have variation seasonally and over years, right? So if you want to go from, say, here, which is, I don't know, 94.8, and you really want to go to 100.0, each unit of energy storage you add gives you a diminishing benefit, because now you have to start compensating for misalignments that occur over longer and longer and longer timescales. And if you want to get to, in the worst case, if you have a 20% overbuild and you want to get to 100% renewables with wind, solar, and storage only, you can require up to 17,000 gigawatt hours of storage. Now, you might look at that and be like, that's pretty unrealistic, because that is. That's an enormous amount of storage, right? Each 1.0%, when you look at 1.0, that's equivalent to 338 million Tesla Powerwall batteries, right? And in this case, we need 3.7. And you compare that to the Tesla Gigafactory, which has an annual production capacity of 50 gigawatt hours per year, mainly for cars. This is not going to work, right? This is not feasible, right? So this is why it's very important to do as many other things as we can to reduce the amount of energy storage that we need. So let's look at a more modest goal where we look at, let's use a mix of resources to meet an 80% renewable goal in 2050. And to tie it in with my first example, let's tie it in with how intelligent your charging management is of electric vehicles, because electric vehicles is going to be a large load, but there's also a lot of opportunities for management, right? So I talked about immediate charging, I talked about smart charging, but I am also going to allow vehicle to grid, which is grid communicative, but also has the ability to allow the vehicle to discharge electricity back to the grid to reduce peak loads, as long as the battery has a surplus, right? So as we go through each of those levels of charging management intelligence, here we get a graph like this. This is the power capacity of the stationary energy storage system required. This is the energy capacity of the stationary energy storage system required as a percentage of your renewable capacity and your annual deliverable renewable energy, respectively. And we get this black line. So basically, to reach 80% renewables, the colors are the renewable penetration. To reach 80% renewables, you need to be on this line. Now, if we don't manage how electric vehicles are charged on the grid, if you want to get 80% renewables, this point here corresponds to about 2.3% of annual deliverable renewable energy, or about 10,000 gigawatt hours. That's still a lot of energy storage, right? And that's because you have to, solar is very peaky. You need to have a large amount of energy storage to be able to hold that and shift it over a day, right? So misalignment's very bad. And most of the energy is going to pass through the energy storage system and incur that round-trip efficiency loss. So if we go to smart charging, we look at the exact same graph. you notice that this black line occurs at a much lower power and energy capacity. This is about 0.6%, which starts to get a bit more reasonable, right? And this is because smart charging aligns itself with when renewables occur. Then there's less energy that has to be shifted by the system. You need less energy storage, right? Now, if we do V2G is interesting because if we allow the vehicles themselves, which are already going to be deployed, to act as stationary batteries, you get a graph that looks like this. And you notice there's no black line because everything here is over 80%, right? So big if, and I put asterisks and capitalize this for a reason, if all electric vehicles do vehicle to grid, you can potentially eliminate the needs for stationary energy storage capacity, potentially, right? But there's a lot of practical considerations to be discussed. The thing is that if you're having trouble getting people to buy into smart charging, V2G is going to be a much harder sell, right? So this is kind of showing it more of a theoretical result of if we really make use of batteries that are going to be deployed already, we won't need as much batteries deployed just for stationary functions. But I don't see this case as being necessarily achievable, but it's toward a direction that we have to go. So this is just an aggregate plot comparing how it evolves when you go from immediate charging to smart charging. You get a big benefit, and then to V2G, you can hypothetically eliminate the needs for stationary energy storage, right? So I want to look at, those gives you some aspect of, or some perspective on the numbers of stationary energy storage that we might need, right? What happens if we actually deploy that much storage from an environmental standpoint? All storage provides benefits by using excess renewables and all of the benefits associated with that, but each of these technologies has their own environmental footprint and health impacts, which are not as well understood on a common comparable basis. And also, storage technologies are being developed and evolving faster than we can understand them from a life cycle standpoint, right? So what I'm going to show you is an example that we have comparing the benefit of deploying a given capacity of energy storage versus its impact on different environmental metrics. So this is a preliminary result, so don't cite this, but what we have here is using vanadium redox flow batteries, we combined life cycle analysis with dispatch modeling of the electric grid to compare this red line, which is the amount of greenhouse gas emissions you reduce on the grid for deploying given capacities of energy storage, which is on the x-axis, and the red line is the benefit. The blue line, which is what is being compared to, is the amount of greenhouse gas emissions that producing that energy storage unit, all the materials extraction, all the transport, and so on, contributes as a function of how much capacity that you have. And what you notice here is you deploy some energy storage, you get a huge benefit, cool, and then it kind of saturates out a little bit, right? But as you deploy more and more energy storage, the embedded emissions and embedded energy associated with that keeps going up linearly. And if you go too far, you get a point where they cross. What that means is that beyond this point, you are actually increasing your net greenhouse gas emissions if you deploy energy storage up to, in this region or beyond. Now, for this result, like I said, this is preliminary, but we saw this crossover at 1,840 gigawatt hours. And that is a threshold that is much lower than a lot of those numbers I talked about earlier for how much energy storage we need to meet these goals, right? And really, the optimal amount of energy storage you want to deploy is where the difference between this red and blue line is at its maximum, which is somewhere in here, right? So in like the 500 or so range. So this is important and really drives home the point of energy storage is great, and we're going to need a very large amount of it, but we really need to do away with the thinking that just deploying an unlimited amount of energy storage is a good idea, right? We really need to do as much as we can and make our systems as smart as they can from load and generation perspective to minimize the amount of energy storage that we need to meet these goals. This is the same graph, but looking at particulate matter emissions, right? And what you notice here is for particulate matter emissions, the crossover point is at a much lower energy storage energy capacity. And this occurs because these results are for California. The red line is displacing natural gas, right? And in California, since the main fossil fuel is natural gas, it's not very particulate matter intensive to begin with, so you don't actually get as much of a relative benefit compared to what you get for greenhouse gas emissions, right? Now, this blue line, now this assumes you're manufacturing these batteries in the same area where you're deploying them, which may or may not be the case. But this blue line with impacts still goes up at the same rate, right, from all these industrial processes and so on. So 780 gigawatt hours, which is where we see the crossover point for this metric, and we've done other kinds of environmental metrics and they have different crossover points. But this is also way lower than some of those numbers that we talked about, right, that we showed earlier. So really drive home the point, we have to make our system smart enough and avoid just relying on energy storage as kind of the fallback catch-all technology. So some overall conclusions, we talked about some unintended consequences. If you deploy plug-in electric vehicles, but you don't pay attention to when they're charging and how that aligns with renewable generation on the grid, you don't get your greenhouse gas emissions reductions that you're hoping for. And if your loads are not flexible, you may need more energy storage to meet the same goal than you would have otherwise. And if you don't take into account this materials and manufacturing contributions to these environmental metrics, there is potential to shoot ourselves in the foot, right, by deploying energy storage to a scale that actually increases emissions on a life cycle basis instead of decreasing them. So some potential solutions, incentivizing load flexibility, and there's a whole talk that can be given on that, so I'm not going to go into details on that. And also including life cycle impacts of energy storage in siting analyses and planning and optimization analyses, right? Or life cycle analysis of all of these newfangled technologies that we want to deploy to large scale, right? As part of the objective function in optimizing the portfolio of future energy resources. And overall, there's many ways by which we can transform the technology portfolio of our energy system. Certain pathways have some issues, right? And we need to do this kind of modeling to be able to identify them, not so that we can get discouraged and not so that we can, I guess, give up, but we have to identify them so that we can avoid them, right? Ignoring them isn't going to do us any favors, and that's kind of what a lot of the research I focus on tries to do. So I'll take any questions.